We're going to go ahead and evaluate and graph polynomial functions. So as you know, a polynomial function is made up of multiple monomials, one or multiple monomials. So for our first example, our first couple of examples actually, we're just going to go ahead and classify these polynomials to quickly review types of polynomials that we could have. So we have number one, f of x is equal to negative 3x to the fourth power minus 3x plus 8. In order to identify the type of polynomial this is, we first have to identify the degree of the polynomial. So as a reminder, degree of a polynomial is the highest exponent on the variable in the polynomial. So our highest exponent here is 4, so the degree is 4. Therefore, this is a quartic. Degree 4 is a quartic. Now let's move on to odd or even. Well, in order to identify whether or not the polynomial is odd or even, you need to identify the leading coefficient first. So the leading coefficient is the coefficient attached to the degree, attached to that highest exponent. So the leading coefficient here is negative 3. Negative 3 is an odd number, so this is an odd polynomial function. We're going to leave off the number of terms here. It's not necessary for this, but if you did want to look at it, then there are 2 operations in this problem. So there's 3 terms, 1, 2, 3. There's always going to be one more amount of terms than there are operations because the operations separate the terms from each other. So you always start with the first term, then an operation. Are you adding or subtracting? And then the next term, operation, add or subtract. Next term, so on and so forth. That can repeat for infinite amount of times. Okay, so in this case, we would say that there's 3 terms in the problem. But we're going to move on to the constant in the problem. The constant is going to be the number that does not contain a variable. So this is positive 8. Positive 8 is the constant. And that is relevant because the constant is actually the y-intercept of the graph. So this particular function is going to cross the y-axis at positive 8. It is the y-intercept, and of course that's the number without the variable, so the constant will not have a variable. All right, let's move on to number 2. We have f of x is equal to 2 minus 4x squared. First, let's identify that this is not in standard form. We can rewrite it in standard form by making sure that the highest exponent comes first. So you would write negative 4x to the second power first because second power is the highest exponent here. Oh, we need that smaller. And then you would write the positive 2 after. So we're switching the order here so that it's in standard forms. Now this is standard form. Highest exponent to lowest exponent. Okay. Now, we didn't have to do that, but it's great to review what standard form is. All right, so since the highest exponent here is 2, then the degree is 2. And degree 2 would be classified as a quadratic function. So this is a U shape. Okay. The leading coefficient, again, is that number attached to that highest degree. So the leading coefficient is negative 4. And negative 4 is an even number, so this is an even function. And lastly, the constant is the number that does not contain a variable, so that's a positive 2. Again, that's the y-intercept of the graph also. Number 3, f of x is equal to 3x minus 1. This is already in standard form. The highest exponent in this problem is 1, so the degree is 1. I know you don't see the 1, but it does exist. It is right there on the x. So when a variable does not have a power, the power is 1. It is not 0, it is 1. Okay? So the degree here is 1, and degree 1 is classified as a linear function. So that is a straight line. Okay? Moving on to the leading coefficient. The leading coefficient is 3. 3 is an odd number, so this is an odd function. And lastly, our constant is -1. Go ahead and try to do number 4 and number 5 on your own. Pause the video and play when you're ready. Number 4. F of x is equal to -3x plus 4 minus x to the third power plus x to the second power. This is not in standard form, so hopefully you rewrote it in standard form, or maybe it wasn't necessary for you and you could already identify that the degree in this problem is 3. 3 is the highest exponent, so 3 is the degree. Now, third degree will be classified as a cubic function. The leading coefficient is the coefficient attached to that highest degree, so that is going to be -1. -1 is an odd number, so this is an odd function. Now, what does odd and even mean? Odd and even is going to, number 1, help us predict the end behavior in the graph, and it also identifies how many curves you might have in the graph. Not the exact number, but it does help you identify like how many curves will be in the graph. But most importantly, end behavior. Knowing the degree and whether or not it's an odd or even function really helps with the end behavior. So that's what we're going to be going into next. So lastly, we have number 5, which hopefully you did on your own. F of x is equal to x's 7th power minus 7. The degree here is the 7th power, so this is degree 7, and we're just going to call that a polynomial. We don't really need any names past quartic. Okay? I mean, really, we can classify these all as polynomials, but it is good to know some of the types of names. So the leading coefficient is +1. Hopefully you wrote that. And that's an odd number, so this is an odd function. Okay? Cool. Oh, did I miss the constant? Sorry. The constant for number 4 was +4. It's the number without a variable, and the constant for number 5 is -7. Okay. Evaluate using direct substitution. Guys, we are not going to be differentiating between direct substitution and synthetic substitution right now, so we're just going to evaluate using substitution. So evaluating function, why do we evaluate functions? It's probably good to know that. We evaluate functions to find points on the graph. So evaluating is to find points on the graph. There's a reason for why we do certain things. Okay, so we'll be able to apply what we're going to learn for number 6 through 8 to actually graph a polynomial on our own. So you're going to have to evaluate the function in order to graph the function on your own. So first, let's just practice evaluating. We'll move on to graphing afterwards. Okay. So it says f of x is equal to 2x to the 5th minus 4x to the 3rd plus x minus 1 when x equals 2. So we're going to evaluate this function when x is 2. So we want these x's to be replaced with a +2. So the first thing I'm going to do is copy the problem again, but we're going to leave the x's blank because we'll be replacing the x's with positive 2. So again, anytime you're going to be doing substitution, make sure that you use parentheses to substitute. So we're writing that f of 2 is equal to 2 times 2 to the 5th power minus 4 times 2 to the 3rd power plus 2 minus 1. Okay? Now, you can evaluate this on your own using PEMDAS, but I'm just going to go ahead and use a calculator. So I'm going to use Desmo's scientific calculator. To evaluate this. So this is what I'm going to plug into the calculator right here, just this portion, right? We can't plug an equal sign into the calculator. We're going to let the calculator do the equating. So we're going to do actually no, if you are not using a calculator and you want to do this on your own, make sure that you do 2 to the 5th power first before you multiply by this 2. Okay, according to PEMDAS, you have to do exponents before you do multiplication. So it is not 2 times 2, then to the 5th power. 2 times 2, 4 to the 5th power. That is wrong. It is not 4 to the 5th power. It is 2 to the 5th power, which is 2 times 2, 4 times 2 again, 8 times 2 again, 16 times 2 again, 32. This is 2 times 32, which is equal to 64, okay? It is not 4 to the 5th power. It is 2 times 32, okay? Just a reminder. But let's go ahead and put this into the calculator, everything we have highlighted here. So 2 parentheses, 2 times 2 to the 5th power minus 4. Make sure that you're doing this calculating part as well with me. Right? Don't just watch the video. Make sure that you know how to use the calculator on your own. So this gave me 33. As you can see, I got 33. So when we're evaluating, we're finding points on the graph. So our final thing that we're going to write here is that the point we just found was 2, 33. So this is the x and the y. The x that we plugged in and the y is what we got out. Number 7. Clear. Okay. We have f of x is equal to negative 2x to the 3rd plus 7x squared minus 5x minus 1 when x is negative 3. So again, we are substituting. Let me move this over a little. We are substituting negative 3 for this x, and this x. So I'm just going to, don't move. Okay. So I'm just going to prepare for that now. Remember that you are going to first rewrite the problem, but just leave space to substitute for x. 7x to the 2nd power plus 5x minus 1 equals. So now let's substitute in negative 3 because they asked for x to equal negative 3. So negative 3 here, negative 3 here, everywhere where we had an x, okay? Again, I'm going to use my calculator for this, and this is the part that I will be putting into the calculator. The whole problem. So negative 2 parentheses negative 3 to the 3rd power plus 7 parentheses negative 3 to the 2nd power plus 5 parentheses negative 3 minus 1. And I got 101. 101 as my answer. So final answer is input negative 3, output was 101. So this is the point on the graph that we just found for this function. Now, of course, in order to graph a function, you're going to need more than just one point. I suggest that for a polynomial function, depending on what the degree is, so if you look at number 7, the degree here is 3. So again, degree is highest exponent. So the highest exponent is 3. So I would suggest having 5 points for this graph. So I would plug in 5 different numbers into this equation. And since you're using a calculator, you really just only have to change the numbers, right? So here, here, and here, since you already have it in a calculator. So that's my rule. My rule of thumb is to look at the degree of the polynomial and go like 2 numbers higher. So if the degree is 4, I will plug in 6 numbers, because the higher the degree is, the more curves your graph will have. So the more numbers you plug in, the more points you will get. So you'll be able to hopefully identify all of the curves that are in the graph. Because if you don't have enough points, you probably will only graph half of the function and you'll be missing the rest of the picture. So that's a tip. Also, space out the numbers that you're plugging in. For example, we just substituted in -3 for this problem. Maybe I shouldn't substitute -4 in next, right? Like, space out the numbers. Instead of plugging in -4 next, maybe I'll do -6 or -7, right? I want to space it out so I can really figure out how large or how far this graph goes. Okay, let me clear the calculator. Number 8, f of x is equal to -2x to the 4th plus 3x to the 3rd power plus 4x squared plus 2 when x equals -1. So now x is going to be -1. There we go. X is going to be -1. Wrong place. So every x I see, I am going to substitute in a -1. So again, rewrite the problem. F of x, we're leaving that blank, is equal to -2 x to the 4th plus 3x to the 3rd plus 4x to the 2nd plus 2. Now, since x is -1, I'm going to go ahead and put -1 here. So f of -1 is going to give me f of -1, another way that you could say f of -1 is that the function at -1 will equal whatever we're about to get from this calculator. So this is what I'm going to put into the calculator, just this part here. So we're putting in -2 parentheses -1 to the 4th power plus 3 parentheses -1 to the 3rd power plus 4 parentheses -1 to the 2nd power plus 2. And I got 1. So this equals 1. Final answer is that this point will be -1, comma 1. There's my x and my y. Remember, the x was given to us, but you can choose your own x's for your graph. Okay, we're going to go ahead and skip 9, 10, and 11 because it's just repeating exactly what we've just done back and forth. And we're going to go ahead and do hold on. We're going to do this shouldn't say 8, 9, and 10. This should say 12, 13, and 14, but that's fine. We're going to use this chart. So I will pause the video and copy this chart down if I were you, or screenshot it, whatever works for you. Because this is end behavior of polynomial functions. So end behavior is just telling you how does the endpoints, and I say that, lightly because there may not even be endpoints. There may be arrows at the end, which says that the graph is going to continue infinitely, but end behavior tells us what the two ends of the graph will look like. So you're going to have a starting point of the graph. You're going to have the left side of the graph, which is the starting point, because we read from left to right. And then you're going to have the ending of the graph, which is the right side. We are able to predict whether the left side, the y values, will be approaching negative infinity or positive infinity on either the left side or the right side, strictly by using the degree and the leading coefficient, or looking at the degree and the leading coefficient. So again, we are able to identify whether the left side and the right side of the graph are approaching, the y values are approaching negative infinity or positive infinity. So fancy way of saying, is it going to point downwards or point upwards? Just off of looking at the degree and the leading coefficient. So let's try to break this down as best as I can. The y values, this reads that the y values will be approaching negative infinity as the x values are approaching negative infinity. This is a fancy way of saying that the left side of the graph, left side, will point down. And so over here, this is a fancy way of saying the right side will point up. Okay? So on the left side, the y values will be decreasing. And on the right side, the y values will be increasing. We are literally able to imagine in our head exactly how the left side and the right side of the graph are going to look, strictly off of the degree and the leading coefficient. Don't worry. It seems like a lot now. It seems a little complicated now, but you will understand with time. So at the top of this chart, you'll be looking at odd degree polynomials. Okay. Odd degree polynomials are always going to have two opposite facing ends. So if the left side is pointing down, the right side will point up. If the left side is pointing up, then the right side will point down. That's how odd degree functions work. Okay? So as you can see on this side, you'll see that left side points up and right side points down. Okay? All right, at the bottom here, you will have even degree functions. Even degree functions, their left and right side, or their endpoints, their y values, are either going to both decrease or both increase. That is how the end behavior will perform or act, whatever, behave. So if the degree of the function is even, both sides will both increase or both sides will both decrease. So as you can see in the picture here, okay, both sides point up, and here both sides point down. And we'll be using this information to draw graphs ourselves or sketch graphs ourselves. So this is actually, you're going to have to learn this at some point, right? So right now you're just being introduced to it, but you're going to have to learn this, memorize this, really know this like the back of your hand at some point. Okay. On the left side of this chart, we're looking at leading coefficients being positive. Okay. So positive leading coefficients can really do anything. Okay. A positive leading coefficient really means that on the right side, the end, I would say, like in quotation, the end of the graph will face up. So by that, I'm saying here, the right side will face up. Okay. Now, on the right side of this chart, sorry. You know, like I'm saying left and right so many times, but on the right side of this chart, you have that, let me use this. You have that the leading coefficient is negative, okay? So what happens with that? Well, if the leading coefficient is negative, then you can see that the right side of the graph will now face down. The end of the graph, right? The end of the graph will now face down. So you could think of it as facing negative. The y values will approach the negatives. The y values will approach the negatives at one point. Yes, they may start off in the positives, but at some point they're just going to keep going negative. Okay? Here we kind of see an increase, then a decrease, then an increase, but at the end it is going to continue to decrease toward the negatives, the negative y values. Okay, so let's go back over here. Leading coefficients being positive means that the end behavior will continue to go towards the positive y values. The end behavior will continue to go towards the positive y values. So remember that the left of a graph is the start and the right of the graph is the end. Start, end. We read left to right, just like you've been reading the words on this screen. We read graphs from the left to the right. Okay, so let me show you how to use this graph, and that's going to be the last part of this worksheet, and then you can do the back on your own. Okay, match the description of the polynomial with its appropriate graph. Okay, we have an even degree with leading coefficient being negative. So the leading coefficient is negative, and we have an even degree. So we're in this situation here. That tells us that both ends of the graph will be facing downwards, okay? We know that the degree is even. We don't know what even number it is. We don't know if it's 2, 4, 6, 8, 10. We don't know that. So we don't know the amount of curves that are in the graph, but we do know that the beginning of the graph will face downward, and so will the end of the graph. Both ends will be pointing down. So we're going to write the end behavior that we see right here. We're going to write that as x is approaching negative infinity, f of x will approach negative infinity. And as x is approaching positive infinity, f of x is still approaching negative infinity. So fancy way of saying both sides point down. Okay, so with both sides pointing down, we're looking at this graph right here. So we're writing A. Next, we have degree is odd and the leading coefficient is positive. The degree is odd and the leading coefficient is positive. Okay. Degree odd with leading coefficient positive. We're looking at this situation here. That means that on the left side of the graph, it's going to point down, and on the right side of the graph, it's going to point up. Again, I don't know the exact amount of curves that are going to be in the graph because they said the degree is odd, but they're not telling us, is that a +1? Is that a +3, 5, 7, 9, 11? Like, what exponent are we working with here? We don't know. But we do know the end behavior of the graph. We know that the left side is going to point down and the right side is going to point up. Okay, so we would look at the correct way of, remember, what I wrote in blue is the breakdown of it, right? But the correct way to write it is that f of x will approach -infinity as x approaches -infinity, and f of x will approach +infinity as x approaches +infinity. Okay, but that is going to be this graph here. So left side pointing down and right side pointing up. Okay. Next, we have degree is even. The degree is even again. And the leading coefficient is still positive. So degree is even and leading coefficient is positive. Now, I'm sure you could figure out we only have one graph left, but let's take this chance to read the chart again and really understand what we're looking at. So degree is even and leading coefficient is positive. That is this situation here. Both sides should be pointing up. So we're looking at as f of x, as x is approaching -infinity, f of x will approach +infinity. So it's pointing up. F of x pointing up. As x approaches +infinity, f of x approaches +infinity again. So again, f of x pointing up. Remember, f of x just means y. Okay, the y values will increase is what this means. Okay, so both sides facing up is B. And that is done. Go ahead and try to do the next worksheet on your own.